All right, we're in chapter 9 of our text, section 2 this time, and question number 13 in the problems. Let's work this one. And as I start looking at it, I see sample data. Where, and I look, I don't see any things already computed like the sample mean or sample deviation. It looks like we're going to calculate that ourselves. What I did to calculate that was put the values into Excel and used Excel functions to calculate the mean and the standard deviation for each of these samples. I'll give you that data here in just a minute. Okay, so let's read this. A county environmental agency suspects that the fish in a particular polluted lake have elevated mercury level. Okay, so we're going to look at a difference, something that's current and something that's more than that. To confirm that suspicion, 5 striped bass in that lake were caught and their tissues were tested for mercury. For the purpose of comparison, 4 striped bass in an unpolluted lake were also caught and tested. The fish tissue mercury levels in milligrams per kilogram are given below. Okay, there are 2 sample sets. Then A, construct a 95% confidence interval for the difference in the population means based on these data. Okay, so we want to do for A, we're going to be looking at, I forgot to mess with my system here a minute. All right, A, so the 95% confidence interval, so my alpha is going to be 0.05. If I look at these, my sample sizes, immediately my sample size of 1 is 5. The sample size of the second one is 4. Both of these are less than 30, so we're in small sample size, which you would expect since that's what the whole section 2 is about, the t-distribution. So we'll be there in just a minute. So for these samples, we'll need to calculate, as I mentioned, so x bar 1, as I calculated that in Excel, that wound up being 0.625, and the sample deviation on this first one was 0.061. And I'm going to just put my number of the sample over here and delete those over on that side so I can put this other information over there. So my x bar 2, the average of this sample, is 0.398. Yeah, that's quite a difference from x1. So S2 is going to be 0.123, and the number in my second sample is 4. With this type of standard deviation, there's a fair difference here between these two. So it may be likely that they're enough different that sample 1 is elevated from sample 2, because, So that's just off the top of your head, just that first look that I do of what's going on there to give you an idea of in what direction may this go as I work this out. Okay, so for our confidence interval, we have 2 things we're going to be needing to look at here. We have these 2 pieces of this long involved equation that we had from this section. So x1 minus x2, the mean, so x bar of both of those, plus or minus, since we're a small sample size, we're going to use the t-distribution. And the square root of this SP squared times 1 over n1 plus 1 over n2. And where this SP squared is this weighted thing here where we have their first sample size times the deviation of that sample plus the second sample size. Both of those are minus 1 times the second sample deviation squared. All that over the sum of the 2 sample sizes minus 2. And this also let us know here that this particular t-distribution is at degrees of freedom, the n1 plus n2 minus 2. Okay, so that's where we're starting, and we're going to have to use the calculate here. So let's start filling in information. Let's calculate over here for our SP squared. So the SP squared is going to equal, okay, n minus 1, so we had 5 minus 1, that's 4, times our, let's see, our deviation, that was 0.061 squared plus, this time we have 4 in our sample size, so 4 minus 1 is 3, times our deviation here, which is 0.123 squared over our 5 plus 4 minus that 2. So our two sample sizes minus 2. Okay, so this equals 4 times 0.0037 plus 3 times 0.015. All that's divided by 7 equals 0.0085 when I worked that all out. Now the first thing I did when I actually started inputting this was I put this in. This is the SP squared, which is the term I'm going to be using over here as squared. First time I did it, I stuck this number in to the SP here and squared it again because I forgot this is the SP squared formula that's being calculated. Okay, so let's go ahead and put our information back in over here. Oh, so you know what? Let's do this first. So our T at alpha over 2, so our 0.05 divided by 2 will be the T is 0.025 degrees of freedom. That's the N1 plus N2 minus 2. So we have that right here. We calculated that a minute ago. That's 7. When I look that value up, that is, let's see, that equals 2.365. So if I start putting my numbers in, my sample 1 mean 0.625 minus my sample 2 mean 0.398 plus or minus 2.365 times the square root of 0.0085 times 1 over my first sample size plus 1 over my second sample size. So I wind up here with 0.227 plus or minus 2.365 times 0.0618 when I work out that the square root, which is going to be 0.227 plus or minus 0.146. So my interval is going to be 0.081 and 0.373. Okay, so that is actually my confidence interval. So I'm 95% confident that the difference is between 0.08 and 0.373. So I'm highly confident that, 95% confident that the difference, that there is a difference greater than 0. Let's look at that. Let's do that from a statistical hypothesis test standpoint then. So we're going to do it at a 5% level of significance. So again, here our alpha is going to be 0.05. And to see if there's sufficient evidence to conclude that fish in the polluted lake have elevated levels of mercury in their tissue. So we're going to be looking at the difference in the means to see if that difference, so our null hypothesis is going to be that the difference is 0. And our alternative hypothesis is that difference is going to be greater than 0. So that it's elevated, meaning that 1 is going to be larger than 2. So when you subtract the 1 from the lower from the larger, it's going to be a positive number. So it's going to be greater than 0. So that's our alternative. So that was step 1 in our hypothesis step-doing procedure. Step 2, which I always add to step 3, is identify the test statistic and then actually calculate it out. So our test statistic, if we go back to the section of the book here, so it's going to be T, which is going to be looking at our difference in our means of our samples. And again, minus the D, in this case, the difference that we're looking at in our naught, D naught, or that difference is going to be 0. Let's see, divided by the square root of SP squared times 1 over N1 plus 1 over N2. And lo and behold, we calculated some of these already up above. So if we look at that, our x1 minus x2, that is right here. And our SP squared, the square root of SP squared times 1 over n plus 1 over n2. That was this thing. So this is going to equal 2.27 divided by 0.0618. Okay, let me get rid of those because I was just getting where we had calculated that. So when I divide this out, this is 1.895. So that's the value of our test statistic. We need to look at determining what the rejection range or that value is. So for this, we want to look at our t and alpha over 2 degrees of freedom. In this case that we calculated, the n1 plus n2 minus 2, this can be 7. So this is our t of 0.025. So that's where we're headed with that. Oh, no, wait. Why did I put that t over 2 here? This is a one-sided test. So let's go back. So t of 0.5 is where we're headed with degrees of freedom there. And so t is 0.5, degrees of freedom 7. I looked that up in the table. And that's 1.895. Why do I have 1.895 back up here? I go back and look at my notes. And actually, if I divide 0.227 divided by 0.0168, I don't get 1.895. I get 3.67. I'd written the wrong number down there. Okay, so we go back here again. So our rejection range, so that's the critical value, the 1.895, means our rejection interval or range is going to be 1.895 out to infinity. So that's where I am. So now if we compare that in 5, the 3.67 is in rejection interval. So we have enough data at the 5% level of significance. So yes, fish in polluted lake have elevated level of mercury according to our data at a 5% level of significance test. There we go, number 13.